back to our problem where we had finished problem B1, where we had a puck colliding with a curling stone. The two didn't stick together, but if we were given the final speed of the curling stone, 1 meter per second, then we found in part B1 that the final velocity of the puck is minus 1 meter per second. In other words, it's going in the negative x direction at 1 meter per second. And the question we're asking now is this an elastic collision? In other words, is the final kinetic energy equal to the initial kinetic energy? And if not, how much kinetic energy is gained or lost? So one thing we can do to answer both these questions is just calculate the change in the kinetic energy. If it were elastic, kinetic energy would be conserved. Let's calculate the change in the total kinetic energy. That's the total final kinetic energy minus the total initial kinetic energy. And we can do that with just adding together the 1/2 mv squared. So that's final kinetic energy. One of them's moving at speed, 3 kilogram puck is moving at 1 meter per second. The 12 kilogram stone is moving at 1 meter per second. So this is the total final kinetic energy. And initially, only the 3 kilogram puck is moving. So this is the initial total kinetic energy because the stone didn't have any. And I subtract off to get the change. And I find a change is minus 6 joules of kinetic energy. So that means the kinetic energy went down by 6 joules. And so the answer is it's not an elastic collision. And in fact, how much kinetic energy is gained or lost? We would say 6 joules of kinetic energy is lost due to thermal, well, in this case, it's lost. Where it goes to, that energy isn't completely lost, but it transforms into something else. When this happens, two objects collide and some kinetic energy is lost. There's a lot of vibration that happens during that collision. That vibration gets translated eventually into thermal motion. So it ends up heating up the two objects. They get warmer when there's an inelastic collision. Some of the initial kinetic energy of those big masses moving is transformed into motion down at the molecular scale, thermal motion of the individual molecules, and we call that a heating process. So in this case, kinetic energy is lost, but it's not really lost. We just can't see it. It's down there at the molecular scale. All right, question B3, again, same situation. If the coefficient of kinetic friction between the puck and the ice is 0.1, how far from the collision point does the puck slide before coming to rest? So we're to take these numbers about the puck's final velocity is 1 meter per second in the negative x direction. How far does it slide? Well, to answer that, we can use our old friend, the work kinetic energy theorem. We'll take our system just to be the puck. In this case, there are 3 forces that are acting on it as it's sliding to rest. The normal force, the weight force, and the friction force. But the normal force and the weight force don't do any work. So it's only the friction force that contributes to the net work. That's all we have to put into this. Normal force and weight force don't do any work because they're perpendicular to the direction it's sliding. And the work kinetic energy theorem says that's equal to the change in the kinetic energy of the puck. That, the final kinetic energy minus the initial kinetic energy. And the final kinetic energy is going to be 0 because we're going to take initial to be just after the collision, final when it's slid to rest. So it's at rest, V final is 0. When we plug that stuff in to calculate the work done by friction, well, first of all, it's negative work. That's why I put the minus sign in there. And it's equal to the force times the displacement. So in this case, the magnitude of the force, the friction force, is mu kinetic times the normal force, and the normal force balances out the weight force, so it's mu kinetic times mg. And the unknown distance that it slides along the direction it's moving, I'm just calling d. Okay, and I plugged in the information about the initial kinetic energy. Initial here means the kinetic energy of the puck just after the collision. That's what I'm calling initial here. And solve for d, and you get d is just over half a meter. On this same worksheet, there are 2 problems, and I'm only going to talk about one of them here, but they're just examples of things that aren't colliding along one dimension. Maybe they're colliding, in this particular case, we've got a car of a certain mass moving along the x direction at a certain speed, and a more massive truck moving along the y direction with a different speed. And in this particular problem, they don't stick together, but we take a measurement of the truck's velocity after the collision. The truck, which was moving in the plus y direction, ends up, after a very quick collision between the two, moving in the plus x direction at 5 meters per second. And the question is, just after the collision, what is the velocity of the car? So these two don't stick together, but they bounce off of each other. In order to have momentum be conserved, what does the final velocity of the car have to be? And so in this case, I drew a little cartoon here. Here's the before situation. Here's the after situation. I've put in the known final velocity of the truck here, but the car has an unknown final velocity. We want to figure out what its x and y components are in this coordinate system, x being to the left, y being up in my picture. So we set the total initial x momentum equal to the total final momentum, and that tells us what Vx final of the car is, and the total y initial momentum is equal to the total y final momentum. That tells me what the final y component of the car's velocity is. So nothing in principle more complicated here than what we've been doing. It's just doing it twice, once for each dimension that you're working in. You know, in general, if you got an asteroid colliding with another asteroid, you'd have to use x, y, and z components to really figure out how things are moving afterwards. All right, let's do, I think, 1 or 2 voting questions. It might be 2. Person, so this is like a carnival game where you're trying to knock down those sometimes bowling pins that have space between them. You're throwing baseballs or softballs at them, and so you're trying to knock them down. You're given a choice between 2 balls of equal size and equal mass. One of them's made of rubber, so it's a bouncy ball, and the other one's made of putty, kind of like clay, so it doesn't bounce so well. So when one hits the bowling pin, it's going to bounce off of it, and the other one is actually going to stick to it without bouncing back. Rubber ball bounces back, the ball of putty sticks to the pin. Which ball, if you throw them with equal velocities, which one's more likely to topple the bowling pin? We have the 2 choices of the 2 balls, there's no difference, or we don't have enough information. A lot of people actually have the wrong intuition about this one because they think, you know, if the ball goes back, it takes some of its momentum with it, whereas the ball of putty, which sort of doesn't go backwards as much, gives as much forward oomph as it can towards knocking it over. But that's not true at all here. In our derivation, one way to see the answer is we're going to use the conservation momentum, but the conservation momentum not in terms of the way we ended up writing it, the total initial momentum equals the total final momentum, but rather a different way to view it is the change in one's momentum is equal to the change in the other's momentum. So here the 2 objects are the ball and the bowling pin. Momentum, in that very quick collision between them, momentum is conserved, and the change in the momentum of the bowling pin is equal to the change in momentum of the ball. So which ball has a greater change in momentum? The one that essentially slows down almost to a stop when it thuds into the pin, that would be the ball of putty, or the one that bounces backward? And this is related to a voting question that we did quite a while ago, but the answer is when something turns around and goes in the opposite direction, it has a much bigger magnitude change in momentum, right? So if the ball is traveling to the left, and then it ends up traveling to the right, it has a huge change in momentum in the direction to the right, and that means the bowling pin has a huge change in momentum to the left. It's likely to topple over. Whereas the ball of putty going to the left almost comes to rest when it sticks onto the bowling pin, and so it only has a moderate sized change of momentum to the right, which means the pin is only going to have a modest sized change of momentum to the left. So in this case, the rubber ball, you want the ball to bounce back, not just stick to it, if you want as much momentum to be transferred to the other object as possible. And that's what we need to happen for it to be knocked over. We want it to start moving in the final state with the greatest possible final velocity. Finally, is it possible for a stationary object that's struck by a moving object, so one object slams into another one at rest, is it possible for the stationary object to have a larger final momentum after the collision than the incoming object had before the collision? And the answers are yes or no. Many people also have the incorrect intuition about this one. It seems like it would violate the law of conservation of momentum, but it doesn't. And that's because, just like in the previous problem, you're probably thinking when something turns around and goes the other way, it doesn't have as big of a change in momentum, but it actually has a much bigger change in momentum. So one way to think of this is, let's imagine a bowling ball here sitting at rest in the initial state, and a ping pong ball, that's a very light object, moving towards it with momentum p. Now, compared to the ping pong ball, the bowling ball is essentially a brick wall. And if we imagine this ping pong ball has an almost elastic collision with the bowling ball, if it collides with a brick wall, it's just going to bounce back and have the same equal and opposite momentum in the final state. So let's imagine that happens. This is a really bouncy ping pong ball. It bounces back with opposite momentum that it came in with. Its change in momentum is 2p. In other words, it's twice the initial momentum. So it changed, since it goes from p in this direction to p in that direction, it changed by 2p in that direction to the left. That means, according to that one statement of the conservation of momentum, that the bowling ball changes its momentum by an amount 2p to the right, equal and opposite changes in momentum. But the bowling ball was at rest, so if it's going to change its momentum by 2p, it has to be moving with momentum 2p in the final state. And that means this one's final momentum is bigger than this one's initial momentum in magnitude. There's no violation of the conservation of momentum there. Notice that the total momentum in this case is p going to the right, because this one is at rest. And in this case, if you add them up, we've got 2p to the right and p to the left adds up to just p going to the right. So momentum is conserved in this case. This does not violate the conservation of momentum. It's just, I'm trying to address people's wrong intuition about how to use the conservation of momentum, because momentum is a vector quantity, and that means things going in opposite directions cancel with things going the other direction. Let's take a break there.